Swayam Prabha. Digital India. Educated India.
This class will see different properties of finite fields and construction of a finite field through an example. So, we will construct the finite field f 2 power 4, that is the extension field of the binary field f 2. We have seen previously that for any prime power p power m, there is a finite field of order p power m. The way we proved it is that you first consider z p and then you take the polynomial x p power m minus x p power m minus x and take its splitting field, and that splitting field is f p power m. But this method, this is a proof technique and it is not a construction method. The construction usually starts by first identifying an irreducible polynomial of degree m over z p. So, let us take f 2, which is 0 1 modulo 2 addition and multiplication, and we want to extend this field by degree 4. So, that we get f 2 power 4. So, for this we want a degree 4 irreducible polynomial over f 2. So, what are the irreducible polynomials of degree 4 over f 2? So, one is x power 4 plus x plus 1. You can check that this is an irreducible polynomial. How do you check this? First of all, note that if you look for degree 2 irreducible polynomial, there is exactly one, x square plus x plus 1. This is an irreducible polynomial, irreducible binary polynomial of degree 2, and there is no other irreducible polynomial of degree 2, because x square plus x is not irreducible. Clearly, it has factors as x times x square plus x is x times x plus 1, then x square plus 1, because f 2 is a characteristic 2 field, it is same as x plus 1 power 2. The power by, if you take power 2 or power 4 or power 8, so powers of 2 as in the power, then that power distributes on each term, because the characteristic of the field is 2. So, this is not an irreducible polynomial, this is not an irreducible polynomial, this one is an irreducible polynomial. So, now let us look for degree 4 irreducible polynomials. X power 4 plus x plus 1 is an irreducible polynomial. You can check that. How do you determine that this is an irreducible polynomial? Note that there is no root first of all, 0 and 1. If you put 0 in place of x, you get 1. If you put 1 in place of x, you get 1 plus 1 plus 1 modulo 2 is 1 again. So, neither 0 nor 1 are roots of this polynomial. However, it may still happen that this polynomial is a product of two degree 2 polynomials. Now, those degree 2 polynomials must be irreducible, because otherwise if you can factor them you will get a linear factor which will mean that there will be a root, but we have already verified that this polynomial does not have any root. So, the only possibility is that it factorizes into two irreducible polynomials of degree 2, but degree 2 there is only one irreducible polynomial which is this. So, it can only be the square of this, but the square of this polynomial is not this polynomial. Square of x square plus x plus 1, that is this times itself, is x power 4 plus x square plus 1, again by the same rule, because we are squaring over this is a polynomial over f 2 which is of characteristic 2, and the powering is also by 2. So, that powering will distribute over every term. So, this is not same as this polynomial, and hence this polynomial is irreducible. Now, x 4 plus x cube plus 1, this is also not same as this, the square of x square plus x plus 1. So, we only need to verify if this has any root. If you put x equal to 0, this is not equal to 0, it is 1. If you put x equal to 1, again you get 1 plus 1 plus 1, which is 1 modulo 2. So, this is an irreducible polynomial, this is an irreducible polynomial. Now, let us try x 4 plus x square plus 1. Of course, this is not an irreducible polynomial because it is the square of this. It also does not have a root, but it is the square of a degree 2 irreducible polynomial. So, this is not irreducible. How about x 4 plus x cube plus x square plus x plus 1? This again does not have a root because it has 5 terms. If you put x equal to 0, it is equal to 1. If you put x equal to 1, again you get 5 modulo 2, which is 1. So, neither 0 nor 1 is a root of this polynomial, but and it is also not the square of this irreducible polynomial of degree 2. So, it is an irreducible polynomial. One can verify, one can check that there is no other possible irreducible polynomial of degree 4. So, we can, to extend the field f 2 to f 2 power 4, we can start with any of these 3 polynomials. We can use any of these 3 polynomials to extend the field. So, let us take one of them, this x 4 plus x plus 1, the first one. So, how do we construct f 2 power 4? We will construct it as the quotient of the ideal. So, we take polynomial ring and we take the ideal generated by f x, where f x is x 4 plus x plus 1. That is, the elements in the field are the cosets of the ideal generated by f x. Now, you can also represent every coset by a coset representative of the smallest degree, and in that form one can write that this field is nothing but the set of polynomials g x, where degree of g is less than 4 and g x is basically a polynomial, a binary polynomial of degree less than 4. And the operation addition is of course coefficient wise just polynomial addition, binary coefficient wise binary addition, and multiplication is modulo f x. For example, so all binary polynomials of degree less than 4 are there in this. So, what are those polynomials? So, 0, 1, then degree 1 polynomials up to degree 3 polynomials. So, degree 1 polynomials are x, 1 plus x. So, let me write as x plus 1. Then degree 2 polynomials, we can take each of these 4 elements and add with x square, then we will get 4 elements of degree 2, x square plus 0, x square plus 1, x square plus x, and x square plus x plus 1. And with x cube, we can take x cube, we can add each of the previous elements, you get x cube plus 0, x cube plus 1, x cube plus x, x cube plus x plus 1, x cube plus x square, x cube plus x square plus 1, x cube plus x square plus x, x cube plus x square plus x plus 1. So, we have total 16 elements which are binary polynomials of degree less than 4. Now, addition is coefficient wise binary addition. For example, if you take x plus 1 and you want to add with this element x cube plus x square plus x, then we get x cube plus x square plus 1. This cancels x and x, this is 2x, but 2 modulo 2 is 0. Now, if you want to multiply, we have to divide by fx if the degree becomes greater than or equal to 4. Now, if you want to multiply two polynomials, let us take the example of x cube plus 1 times x square plus 1. If you want to multiply, we will get x power 5 plus x cube plus x square plus 1. So, you have to divide that by this x power 4 plus x plus 1. So, you take x power 5 plus x square plus x. So, if you add, we get x cube plus x plus 1. So, this is the product. So, this is x cube plus x plus 1 mod f x. So, this is the polynomial, that is the product of these two polynomials. So, this polynomial is listed here among the elements. Now, we have seen in the last class that there is a primitive element in every finite field. So, can you identify a primitive element in this representation of the finite fields? So, if you take for example, the element x and let us see if the powers of x give us all the non-zero elements, that means whether x generates the multiplicative group. So, let us take alpha equal to x and see whether its powers give us all the elements. Then alpha square equal to x square, alpha cube equal to x cube, alpha 4 equal to x 4, but this is when you divide by x 4 plus x plus 1, it becomes x plus 1. So, this is the element x plus 1, then alpha power 5 we multiply by x every time. So, it becomes x square plus x, alpha power 6 is x power 3 plus x square, alpha power 7 equal to x 4 plus x cube. Again when we divide it by x 4 plus x plus 1, this is x cube plus x plus 1, alpha power 8 is x 4 plus x square plus x, and again when we divide by x 4 plus x plus 1, we get x square plus 1, alpha power 9 is x cube plus x square, alpha power 10 is x 4 plus x cube, which is when divided by x 4 plus x plus 1, the remainder becomes x cube plus x plus 1. Alpha power 11 is x 4 plus x square plus x, which is when divided by x 4 plus x plus 1, the remainder becomes x square plus 1. There is an error here because x square plus 1 cannot appear 2 times. So, I made a mistake here, that this should be x. When you multiply x square plus x 1 by x, it becomes x cube plus x, not x square. So, next one will be x square here, and then when we divide that by x 4 plus x plus 1, we get x square plus x plus 1. And then the next one we get x cube plus x square plus x. So, we can continue. Alpha power 12 is x 4 plus x cube plus x square. When we divide by x 4 plus x plus 1, it is x cube plus x square plus x plus 1. Alpha power 13 is x 4 plus x cube plus x square plus x, which is when divided by x 4 plus x plus 1, we get x cube plus x square plus 1. Alpha power 14 is x 4 plus x cube plus x, when divided by x 4 plus x plus 1, we get x cube plus 1. And then alpha power 15 multiply by x, we get x 4 plus x. When divided by x 4 plus x plus 1, we get 1 as remainder. So, of course, it is quite expected that if you take any element, its 15th power will be 1, because the size of the multiplicative group f to power 4 star, that if you remove the 0 element, it has 15 elements. The order of the group is 15. So, any element power 15 is 1, the identity element. But we see that for this element x, you take the powers, 15 is the first time that it gives us 1, 15 power is the first power that gives us 1. So, it generates all the non-zero elements in the field, it generates the whole multiplicative group. So, x is indeed a primitive element of the of this finite field. Okay. Now, whenever this happens, that we construct a finite field using a polynomial x 4 plus x plus 1, and x is a primitive element in that construction, then we say that x 4 plus x plus 1 is a primitive polynomial. X 4 plus x plus 1 is a primitive element. That is, it is an irreducible polynomial and x is a primitive element sorry, primitive polynomial. This is a primitive polynomial, and x is a what it means is that x is a primitive element in the field f2 power 4 when constructed, that is f2x by x power 4 plus x plus 1. When you construct this extension field in that representation, in that way of constructing, x is a primitive element. Now, there are of course other primitive elements, because this is a cyclic group and x is a generator, and any cyclic group may have many generators, and exactly how many generators are possible, that we have discussed before. If you have a cyclic group, G is a cyclic group with of order of G equal to n, then the number of generators. So, G is cyclic, clearly is generated by A. Number of generators is the Euler's phi function evaluated at n, phi of n. And what is that? It is, you basically take all the prime factors n times product of 1 minus 1 by p, or in other words, if where p divides n is a p prime, that is in its prime factorization. If you write n equal to p1 power, let us say k1, p2 power k2, etc., up to pr power kr, then phi n is, we have seen that this is p1 power k1 minus 1 times 1 minus p1, like this. For every prime number you do this, and then pr power kr minus 1 times 1 minus pr, that is the product over 1 equal to 1 to r, pi power ki minus 1, 1 minus pi. So, exactly so many generators are there, and what are the generators? As you know, the Euler's phi function gives us the number of integers less than n which are relatively prime, which are co-prime to n. And indeed, if alpha is a generator of the group, then alpha power I is also a generator of the group, if and only if I is co-prime with n. So, alpha I G equal to this is generated by alpha I if and only if I, the GCD of I with n is 1. So, here all those powers of x which are co-prime with 15 are also primitive elements. This is a primitive element, alpha square is a primitive element because the order of the group is 15 and 2 is co-prime with 15. 3 is not a primitive element, x alpha power 3 is not, alpha power 4 is a primitive element, alpha 5 is not, alpha power 6 is not, because 6 and 15 have a common factor, alpha power 7, alpha power 8, alpha power 9 is not, alpha power 10 is not because it has 5 as a common factor, alpha power 11, 12 is not, 13, 14. So, how many prime factors are there? 1, 2, 3, 4, 5, 6, 7, 8. 8, and you can evaluate the Euler's phi function for 15, and you will see that it will also be 8. Now, in this field we will also identify its subfields. What are the subfields of f2 power 4? We have seen previously that f2 power, first of all note that for any f p power m, its subfields are also of the same characteristic. So, they will be of the form f p power something. So, when is f p power m a subfield of f p power n? This is a subfield if and only if m divides n. This we have seen last time. So, we are now talking about f 2 power 4. This is what we have. So, you can take the factors of 4 and you will get the subfields. So, its subfields are f 2 power 1, because 1 is a factor of 4, that is f 2, and f 2 power 2, this is a subfield. So, can we identify the elements of these subfields in this field as powers of alpha? So, first of all, for f 2 it is very simple, we see that there is only one non-zero element, that is 1. So, that is alpha power 15, which is 1. So, 1 and 0. So, for any so for f 2 power 2, for f 2 power 2 now there are 4 elements, 1 is 0, the other 3 are non-zero elements. So, there is a cyclic group of 3 elements, right. The non-zero elements of f 2 power 2, because it is also a finite field, its non-zero elements form a cyclic group. So, now here we have a cyclic group of order 15. What is that cyclic group? In f 2 power 4, you can write the elements as 0, 1, alpha, alpha square, alpha cube up to alpha power 14. Alpha power 15 is same as 1. So, these are the non-zero elements, this is the multiplicative group, and then there is a 0 element. Now, in this first 2 elements form f 2. Of course, 1 will be there in any subfields, but in f 2 power 2 there will be 2 more non-zero elements, and including 1 there are 3 non-zero elements in f 2 power 2, and they form a subgroup of 3 elements in this group of 15 elements. Out of these 15, we have to identify a subgroup of 3 elements. And what are those? Well, you can just take alpha 5, you divide 15 by 3, you get 5. So, 1 which is alpha power 0, then alpha power 15, alpha power 5 and alpha power 10. These are the 3 non-zero elements, and then you take 0. These give you f 2 power 4. So, this is f 2 power 2. There are 4 elements. So, in fact, if you take for example f 2 power 6, this will, its elements can be always written in terms of a primitive element as 0 and then all the powers of the primitive element. Suppose alpha is a primitive element, then we can write as 1 alpha, alpha square up to, how many elements are there? 2 power 6 is 64. So, 64 elements are there including 0. So, if you exclude 0, there are 63 elements. So, 1 is alpha power 0. So, alpha power 0, alpha power 1, alpha power 2 up to alpha power 62. So, that becomes 63 non-zero elements. These are the elements of f 2 power 6. Now, if we want to identify the subfield f 2 power 3, 2 power 3 is f 8. What will be the elements? So, you have to have 0 and then a cyclic subgroup of this multiplicative group of order 7. 7 divides 63, the order of this is 63, 7 divides 63, so 63 by 7 is 9. So, you take alpha power 9, the subgroup generated by alpha power 9 will have exactly 7 elements. So, those are the 7 elements that will come here. So, 1 alpha power 9, alpha power 18, alpha power 27 etc. up to power 9 times 6, that is 54. These are the powers of alpha power 9. So, that is F8. So, this is the way to identify the subfields of a given finite field in terms of the primitive elements, in terms of a primitive element. We have also seen that a finite extension is always, for a finite field extension, it is always a simple extension. That is, it is obtained by adjoining one element to the base field. So, when we did this construction f2 power 4, we extended f2 to f2 power 4. Can we say that this f2 power 4 is obtained from f2 by just including one element and then all the required elements are added to make it a field? So, and in fact, our proof was based on the fact that this can always be taken, that element can always be taken as a primitive element. So, in this case, if you take x, once you put this element alpha equal to x, you will get that. So, not only that, so all these 8 elements which are tick marked here, these are primitive elements. So, you can say that this field, same field can be obtained by adjoining any of these elements. Not only that, you can also adjoin in fact alpha power 3, though this is not a primitive element. You can adjoin alpha power 3 and get this same field. So, it is not a primitive element, but you can see that alpha power 3, if it is alpha power 3 is there, then alpha power 6, its powers will be there, alpha power 6, alpha power 9, alpha power 12 will be there, and in fact, these form a basis of f2 power 4 over f2. And we will see later that in fact, they are the roots of this polynomial as well, x power 4 plus x square, x cube plus x square plus x plus 1 this. So, if we construct this field in the same way by taking this irreducible polynomial instead, we will see the same phenomenon that x is a primitive element. Hence, these two are primitive polynomials. They are irreducible, but they are not only irreducible. If you construct the finite field using any of them, x will be a primitive element. But if you do that with this irreducible polynomial, we will see that x is not a primitive element in that field. So, in fact, here, so you know that x is the root of the polynomial which is used to extend the field, and in this case that x corresponds to alpha 3 here, which is not a primitive element. So, we will quickly do that. So, you can see that if you take f x equal to x 4 plus x cube plus x square plus x plus 1, and you take alpha equal to x and you take powers of it modulo this polynomial, we will not go up to alpha power 15, before that we will reach 1. So, you will see alpha square is x square, alpha cube is x cube, alpha 4 is x 4, which is modulo this polynomial, it becomes x cube plus x square plus x plus 1. Then alpha power 5 is x power 4 plus x cube plus x square plus x, but when you divide by this, the remainder is 1. So, you see that the order of the group generated by alpha, this is 5, because there are 5 elements. You get 1 alpha, alpha square, alpha cube, alpha power 4 generates a subgroup of order 5, not the whole multiplicative group of order 15. And in fact, what was the, so this is not a primitive element, this alpha is not a primitive element. In fact, the corresponding elements, the subgroup of order 5 in the previous representation was exactly the powers of alpha power 3, because alpha power 3, alpha power 6, alpha power 9, alpha power 12 and 1, they form the subgroup of, this is the subgroup of order 5 for the multiplicative group, subgroup of the multiplicative group of order 5. So, we have seen in this lecture how to construct a finite field starting with an irreducible polynomial, and sometimes you will have that this x itself is a primitive element, sometimes not. When x is a primitive element, then that irreducible polynomial which we use to construct the field is called a primitive polynomial. Then we have seen how to identify the subfields of the finite field when in terms of a primitive element. We have also seen how to identify all the primitive elements if we are given one primitive element. Those powers of the primitive element which are co-prime with the order of the cyclic group, which is this -1, the order of the field -1.
We will now look at irreducible polynomials and their roots. We will see that over finite fields, irreducible polynomials have roots which have a certain relation. So, first of all, here is the structure, here is the relation between roots. Suppose we have an irreducible polynomial over f q, f x, this is irreducible, and alpha is in some extension field of f q, let us call it f q power m, is a root of f x. Then alpha power q is also a root of f x. So, this is very interesting because once you know one root of an irreducible polynomial, this tells you how to find the other roots. You just raise it by power q and then you can again raise it by power q and so on to get all the roots of that irreducible polynomial, as we will see next. So, let us first prove this. Suppose f x is given as a n x power n plus a n minus 1 x power n minus 1 plus a naught, then f of alpha is 0 means that a n alpha power n plus a n minus 1 alpha power n minus 1 plus a naught equal to 0. Now, we raise this both sides of this equation by power q, then we get a n x power alpha power n plus a n minus 1 alpha power n minus 1 a naught, this power q is equal to 0. Now, because the characteristic of the field is the q is a power of the characteristic of the field, powering by q gets distributed over different terms of the sum, which means the power q comes to a n alpha power n whole thing power q plus a n minus 1 alpha power n minus 1 power q plus a naught power q equal to 0. Now, a n alpha power n power q is same as a n power q alpha power n q, a n power q alpha power q n plus a n minus 1 power q alpha power q n minus 1 plus a naught q equal to 0. But a n's are from f q. So, these a i's are from f q for all I, and because of that a n power q is same as a n. So, a n alpha power q n plus a n minus 1 alpha power q n minus 1 plus a naught power q equal to 0, and that means that this alpha power q is a root of f, alpha power q is 0. So, that is alpha power q is a root of f x. Okay. So, what it means is that once we have one root, then its qth power alpha power q is a root. Again you can take qth power of that, which gives us q square. Again we can take qth power alpha power q cube. All these are roots. Now, of course, it cannot go on forever because f x has a degree, and so it must start repeating after some time. So, let us say the degree of f x is m, then it will go till at most q power m minus 1. After that alpha power q power m must be same as alpha, but maybe that may happen even before. So, what is it? Can it happen even before, or is it true that all these are distinct? If these are all distinct, if where m is the degree of f, then if these are distinct, then we will get all the roots of f this way, because f can have at most m roots and there are m roots here. So, if these are all distinct, then these are the roots. So, next lemma we will prove exactly this, that if alpha is a root of f and degree of f is m, then alpha power q square alpha power q power m minus 1, these are the roots of f. We already know that all these are roots, the only thing is some of them may be same. So, we need to show that these are distinct. So, we know that the field obtained by adjoining alpha to f q, this is f q power m, which means that this index, this degree of extension is m. So, which means that f q power m is the smallest field in which alpha is there. Okay. Of course, in any extension field of that also alpha will be there, but m is the f q power m is the smallest field. This is f q power m, this is the smallest field in which alpha is there, smallest extension field of f q where alpha is there. Now, we know that any element, let us call it say alpha itself, alpha power q power n equal to alpha. This means that alpha is a root of x power q power n minus x, and which is if and only if alpha belongs to f q power n. This is an if and only if condition. Okay, because all the elements of f q power n are exactly the roots of x power q power n minus x. So, alpha is a root of this if and only if alpha is in this. So, now here because this says that m f q power m is the smallest extension field of f q where alpha is there, it means that m is the smallest positive integer such that alpha power q power m is equal to alpha, okay. Which means that certainly after this this sequence alpha power q square etc., it goes to alpha power q power m minus 1, and then alpha power q power m is same as, this is same as alpha, that is this one, it comes back to alpha. But can it happen that for the first time it comes back to alpha from the mth term, but in between also some terms repeat? Can it happen? Now, we will see that that cannot happen. The first time it comes back somewhere, it will come back to alpha itself. So, in other words, if we take any I less than j, two indices here I and j here, so that this is j is less than m, such that alpha power q power I is equal to alpha power q power j, then I must be equal to j. So, you can prove this very easily. We just raise this both sides by power m minus q power m minus j, alpha power q power j, q power m minus j, and then the left hand side becomes alpha power q power m minus j minus I equal to, the right hand side becomes alpha power q power m, which we know to be alpha power 1, because alpha power q power m equal to alpha from here, So, now this says that this power, this is a smaller number than m, and this is a contradiction, because here we said that m is the smallest number for which this can happen, but here this is happening for a smaller number which is m minus j minus I. So, this is a contradiction. So, this cannot happen. Okay. Now, we can restart. Now, we will see the things that we have learned just now through some examples. So, what we have seen is that basically if you have an irreducible polynomial of degree m, then it has exactly m roots, and those roots are obtained from just one root by powering by q again and again until it repeats. We will get m roots like that, and then after that we will come back to the first term. That is how we can get all the roots of an irreducible polynomial. Now, let us see this through an example, the example that we have already discussed before. This is f q power x, this is an implementation of f2 power 4 as f2 x modulo x4 plus x plus 1. We took this irreducible polynomial and took all degree less than 4 polynomials under multiplication modulo x4 plus x plus 1. Now, here these are the elements, alpha equal to x is a primitive element, and we will see all the irreducible polynomials of degree 4, degree 2, and see what are their roots. So, let us start by taking this same irreducible polynomial that we used to construct the field x4 plus x plus 1. So, let us take f x equal to x4 plus x plus 1. What are its roots? Its roots are alpha, then we can power by 2, because we are considering f2, f4 is an extension, f16 is an extension field of f2, that is f2 power 4. So, we power by 2 to get all the other roots. So, alpha square, then alpha 2 square, which is alpha 4, and then alpha 2 power cube, which is alpha 8. These are the roots. Now, let us verify this. So, let us take f of alpha. This is alpha power 4 plus alpha plus 1, which is same as x 4 plus x plus 1, which is 0 modulo x 4 plus x plus 1. F of alpha square is alpha square power 4, which is alpha power 8 plus alpha square plus 1. Now, what is alpha power 8? We can see here alpha power 8 is here x square plus 1, x square plus 1, and alpha square is x square plus 1, which is 0. F of alpha power 4, which is alpha power 4 which is alpha power 16 plus alpha power 4 plus 1, alpha power 16, alpha power 15 is 1. So, alpha power 16 is alpha plus alpha power 4 plus 1, which is also 0, because it is x 4 plus x plus 1, and f of alpha power 8 is alpha power 8 times 4 is 32 plus alpha power 8 plus 1, alpha power 30 is 1. So, it is alpha square plus alpha power 8 plus 1, and this we have seen this is the same as this term, which is equal to 0. So, you see that these are indeed the roots of this polynomial. Now, we will erase this and we will look at another polynomial of degree 4. There is exactly one another polynomial of degree 4, which is x 4 plus x cube plus 1, and its roots are alpha power 7, then 7 times 2, which is 14, then 14 times 2 modulo 15 of course. So, 28, then modulo 15 is 13, alpha power 13, modulo 15 because alpha power 15 is 1, and then 13 times 2 is 26, modulo 15 is 11. So, alpha power 11. Now, you can verify that these are indeed the roots. So, let us verify just for one in this case, others you can do it yourself. So, f of let us say alpha power 14, okay, what is this? So, alpha power 14 power 4, that is 14 times 4 is 56. So, alpha power 56 plus alpha power 14 times 3, 42 plus 1. Now, what is this? Alpha power 56, alpha power 15 is 1. So, 15 times 3 is 45, we can remove, and the remainder is alpha power 11 plus, from here it is alpha power 30 is 1. So, alpha power 12 plus 1. Now, what is alpha power 11 and what is alpha power 12? X cube plus x square plus x, here this is alpha power 11, x cube plus x square plus x, and alpha power 12 is x cube plus x square plus x plus 1, x cube plus x square plus x plus 1, and then plus 1. So, you see that every term is there 2 times. So, they all cancel each other and we get 0. This way you can verify that these are indeed the roots of this polynomial. Now, we will, so these are the degree 4 polynomials. Now, we will take a degree 2 polynomial. X square, actually there is another degree 4 polynomial, f x is x 4 plus x cube plus x square plus 1, and its roots are alpha power 3, then 3 times 2 alpha power 6, 6 times 2 alpha power 12, and then 12 times 2 24 modulo 15 is alpha power 9. These are the roots. Again, we can verify these very easily, just like we did for the others. Now, we take a degree 2 polynomial, which is x square plus x plus 1. Its roots are alpha power 5 and alpha power 10. It is degree 2, so it has exactly 2 roots. Again we can verify this, that this is indeed a root. Say let us take alpha power 10 for example, f of alpha power 10 is alpha power 20 plus alpha power 10 plus 1, 20 is alpha power 5 plus alpha power 10 plus 1, alpha power 10 plus alpha power 5 plus 1. So, alpha power 10 is x square plus x plus 1, alpha power 5 is x square plus x, and then 1. If you add all of them you get 0. So, this is equal to 0. Now, there is only one irreducible polynomial of degree 2 and that is this one. Then we have degree 1 irreducible polynomial. In a moment we will see why we are taking these particular degrees 4, 2 and 1. So, f x equal to x plus 1 is one irreducible polynomial of degree 1 and it has the root 1, and f x equal to x is another irreducible polynomial of degree 1 and it has root 0. So, these are the, now you see that we have all the elements of f 16, there are 16 elements, 4 here, 4 here, 4 here, 12, 13, 14, 15, 16, there are 16 elements. Now, so all the roots, the f 16, the elements of f 16 are all here, they are the roots of irreducible polynomial, they are minimal polynomials of irreducible polynomials of degree 4, 2 or 1. This is what we find. Why is it happening like this? It is because f 16 is f 2 power 4. All the factors of 4 will be the degrees of the minimal polynomials. So, factors of 4 are 4, 2 and 1, those will be the degrees, and those polynomials will be elements of subfields of f 2 power 4. In this case, for example, this alpha 5, alpha 10 are elements of f 2 square, this is a subfield, and these are 0 and 1 is a these are from the further subfield f 2. So, this is a chain of subfields and these are elements in those chains, these subfields. Now, what do you think we will get if we multiply all these irreducible polynomials, these 6 irreducible polynomials? If you multiply, what will you get? You will get a polynomial whose roots are exactly all the elements of f 16. So, what is that polynomial whose roots are, which will be of degree 16 exactly, because these are degrees will just add up 4, 4, 4, 2, 1, 1. Okay. So, 16, and what is that polynomial? We know already that that polynomial is x power 16 minus x, that is x power 2 power 4 minus x. If you multiply all these polynomials, we will get this polynomial or this, and its roots are all the elements of f 16. Now, we see that each of these polynomials thus divide x 16 this x power 16 minus x. So, if you take any irreducible polynomial f x of degree m, we know that it will f x will divide, then f x will divide x power q power m minus x, this polynomial, and for any multiple of m also f x will divide that. For any multiple, f x will divide x power q power n minus x if and only if m divides n. So, this is the now some of these results we will prove mathematically, but we see from this example that this is what is happening. For example, if you take the degree 2 polynomial here, you see that because 4 is a multiple of 2, its roots are there in f 16 also, they are there in the subfield f 2 square, that is f 4, but they are also there in f 16, and hence that f x divides x power 4 minus x but it also divides x power 16 minus x. In particular, this also divides this polynomial, and f x divides this if f x is x square plus x plus 1, this irreducible polynomial. Okay. So, to summarize, what we have seen is that if we have an irreducible polynomial over a finite field f q, then its roots can be obtained from one root. If we have alpha as a root, then the successive powering of the root by q, we get all the roots, and the number of roots that we will get is exactly m, that is the degree of the polynomial. They are distinct roots, and the polynomial, a polynomial, irreducible polynomial of degree m divides x power q power m minus x, and also for any n which is divisible by m, it divides x power q power n minus x. Okay, thank you.